Hello, everyone. I'm David Haig, and the title of my talk is Exploring the Interdependencies Between Transmit Waveform Ambiguity Function Shape and Off-Axis Bearing Estimation. This work was done in tandem with my colleague, Matt Tidwell, and this work was sponsored by the Office of Naval Research. Now, the main theme of this work is about active sonar off-axis bearing estimation, and the principle behind off-axis bearing estimation is that if you have a projector transducer with a known beam pattern and you transmit waveforms with a known spectrum, you can actually control the angle at which the Fisher information for the target bearing estimate is maximized. Moreover, you can do this without shifting or moving the main response axis of the transducer itself. Now, previous efforts by my colleague Matt have shown that for narrowband linear FM waveforms, the angle of maximum bearing precision is solely determined by the LFM's center frequency. What we wanted to look at in this talk was what happens if we transmit different types of waveforms. They may have different ambiguity function shapes and different types of modulation functions. Is there any impact on the off-axis bearing estimation problem? Additionally, since the transducer will induce spectral filtering on the return echo, we're interested in knowing what kind of perturbations we'll encounter in that returned echo, namely in the ambiguity function shape. So it's about the interplay between those two issues. Now here's a brief overview of the waveform signal model. So my waveform is some rectangularly windowed complex exponential with instantaneous phase via t and some carrier term f sub c. This is over the domain of time between plus or minus capital T over 2, the pulse length of the waveform. The modulation function is the first time derivative of a phase divided by 2 pi. And since we'll assume a match filter or correlation receiver, which gives us the range Doppler information of the target scene, we care about the ambiguity function. And in this case, it's the narrowband model. So we're correlating the waveform with its Doppler shifted versions, where our Doppler shift nu is given here. R dot is the target range rate or relative velocity between the platform and the object. C is the speed of sound in the medium, and FC is the carrier term. This work assumes some broadband directional projector radiates acoustic energy into the medium. That acoustic energy then insonifies a point scatterer, and the resulting echoes are received by an omnidirectional hydrophone. We can exploit the characteristics of the received echo to infer certain information about the target. Specifically, we're interested here in estimating the target's angular location based on the spectral filtering the echo undergoes due to the frequency-dependent beam patterns of the projector. So to see what I mean by that, let's consider a target that's right on the main response axis. These beam patterns are for lower, medium, and higher frequencies. Now, in this case, the beam patterns emit basically a constant response across frequency. We get an all-pass-like characteristic shown here on the right. Now, for a target in the blue path, the low frequency beam pattern still has a stronger response, but the medium frequency, we're further along on that beam pattern and we get a lower response. And we actually seem to maybe hit a notch in the high frequency case. So we get this low pass filter type characteristic. Now, for the target on the green path, still we get a strong response in the low frequency case, but we hit a notch in the medium frequency and then exist somewhere in the side lobes in the high frequency case. And we get this sort of notch filter type response. And so we see here that the frequency dependent beam patterns encode information about the target's angular location with respect to the main response axis. So that's what's going on conceptually. How do we translate that to a rigorous signal model? So we see here that the received echo Y, received through frequencies F1 through Fn, being returned by the target at some unknown varying angle theta, is simply a scaled version of the product of the transmit waveform spectrum S of F1 through Fn, and is being weighted by the transducer's beam pattern, which is also frequency dependent. And of course, this is embedded in additive white Gaussian noise. The signal model has two unknowns. Theta is the unknown bearing of the target we wish to estimate, and then we have this unknown amplitude A. The amplitude A is a nuisance parameter in the sense that we don't wish to directly estimate it directly, but its existence hinders our ability to estimate the unknown target bearing theta. Now, previous work by Klepper et al. Actually derived the Cray-Morrell lower bound for the variance on the estimate of the target bearing angle theta, and that's given here. It's a product of the signal-to-noise ratio, this sensitivity term, and an orthogonality term. And if we take the inverse of this, we get the Fisher information, which is the metric that we'll be using as it provides a measure of precision, as a more intuitively analogous representation towards precision. If we minimize the variance, then we maximize the precision. Now, the motivating observation here is that the Fisher information and thus precision of our target bearing estimation problem is a function of the true target bearing. This gives rise to the idea of a sweet spot or an angle at which the Fisher information is maximized. Now, this expression is perfectly general. It makes no assumptions about the transmit waveform spectrum or the projector's beam pattern. So to reduce the degrees of freedom in the problem, Matt had to make some design choices in order to evaluate this technique. And so this is what he did. So he used a continuous line source transducer, which has a sync-like beam pattern. And he transmitted, as I mentioned earlier, narrowband linear FM waveforms. These have two parameters to consider, the lower and upper frequencies that you sweep through in the modulation function. Now, what Matt was able to show was that for narrowband or high Q LFM waveforms, where Q is greater than, say, 3 or 4, the bearing that maximizes the Fisher information is directly proportional or derived from the center frequency, the midpoint between the lower and upper frequencies. Now, what we want to do is examine the same sort of problem, except now we want to utilize different waveforms other than an LFM. They may have different spectral or ambiguity function characteristics and certainly different modulation functions. And we want to have a wide variety of waveforms to see if this generally holds, at least for the narrowband case in the off-axis bearing estimation problem. And so this work focuses on the multitone sinusoidal frequency modulator or multitone SFM waveform. Simply stated, this waveform has a modulation function that's expressed as a finite Fourier series. And I'll examine two different types of waveforms, the kinds with even symmetry in their modulation function composed solely of cosine harmonics, and odd symmetry composed solely of sine harmonics. Now, if we integrate and multiply by 2 pi, we get the instantaneous phase of these two waveform types, which are now a superposition of sine functions and cosine functions, respectively, weighted by these alpha and beta sub k, which are related to those Fourier coefficients. These are the modulation indices. And they represent a discrete set of parameters that we can adjust to synthesize waveforms with a wide variety of properties. And I described how to do that in a recent paper, IEEE Transactions on Aerospace and Electronic Systems. So here's an example of what these waveforms can look like. So in this case, I started by initializing the design coefficients with random values and scaled them so that the waveform occupied a desired band of frequencies. So the pseudo-random modulation function produces a waveform with what's known as a thumbtack ambiguity function. That is to say, a distinct main lobe at the origin and the rest of the volume, which is bounded to spread evenly in the range Doppler plane, resulting in a pedestal side lobes. Now, this isn't the only type of ambiguity function you can realize with this waveform. You can make them Doppler tolerant, something in between Doppler tolerant and sensitive, and a whole host of other types of characteristics. And that's what we wanted to focus on for the off-axis bearing estimation. We want to answer the question of whether the parameterization of this model has an impact on off-axis bearing estimation. So what we're going to do is employ the same sort of model that Matt had implemented earlier, except now we're going to look at the waveform spectrum of the multitone SFM and see what its impact is on the off-axis bearing estimation for both the case where we're utilizing either even or odd symmetry in the waveform's modulation function. So what we found was, while the parameters of the multitone SFM waveform in the narrowband regime have a negligible impact on off-axis bearing estimation, it turns out that the symmetry of the modulation function does. So what we're showing here is weighted mean frequency deviation and deviation in the angle that maximizes Fisher information for a set of trials of multitone SFM waveforms that employed either cosine or even symmetry in their modulation function, or sine on symmetry in their modulation function. There are 1,000 waveforms for each case. With the even symmetric case, what we found was there's a deviation in mean frequency and a corresponding deviation in the angle that maximized the picture information. The reason why this happens is that even symmetric modulation functions produce waveform spectra that are non-symmetric, and that non-symmetry results in a deviation in the mean frequency or shifts the carrier frequency. Now you can offset that by shifting the band of frequencies this waveform sweeps through so you can get the desired center frequency or the appropriate angle that maximizes your picture information. On the other hand, waveforms with odd symmetry in their modulation functions have zero deviation in their mean frequency. This behaves just like the LFM, which is also an even symmetric spectrum. So we also looked at the transducer's spectral filtering impact on the waveform echo. And since the waveform is sweeping through that band of frequencies in an oscillatory fashion, the frequency-dependent filtering of the transducer combines to introduce these AM effects into the echo. And when you correlate that with the original transmit waveform, as you do in an ambiguity function, you get a perturbed ambiguity function. And that's what we're showing in these top two panels. Here's the original waveform's ambiguity function and the perturbed version. And you can see these sort of like striation patterns, and that's a direct result of the amplitude modulation. So if we look at the zero Doppler and zero time delay cuts, which I'm showing below in these two panels, you get a better picture of what's going on. So there's a changing in the main lobe, actually a narrowing of the main lobe in range or time delay, and the side lobes start to pop up here and in other locations. Additionally, in Doppler, while the main lobe didn't really change all that much, clearly the side lobes started to pop up. So these perturbations are pretty noticeable, and so you'd have to do some sort of equalization to try to offset them. So to briefly conclude, for multi-tone SFM waveforms operating in the narrowband regime, the main determining factor that has an impact on off-axis varying estimation is the symmetry of the modulation function, as we described earlier. Additionally, the spectral filtering from the transducer can impact the echo and introduces AM effects to it, which can perturb the desirable ambiguity function properties that you may have encoded in the original waveform. And so you'd have to likely develop some equalization techniques to offset those perturbations. So this concludes my talk. Thank you very much.